Uh, Hello everyone, my name is Vijayanth. I am from India and I presently work at RF Systems. For the last 2 years or 3 years, I guess, I've been looking into solid design principles mainly because I got interested in what interfaces are all about. And once I started looking into interfaces, solid design principles are very closely tied in there. So I started exploring them. And for the last, I think, after understanding them and sort of using them in my code, I found my the quality of my code has improved. So I suppose for the next 45 minutes, I'm going to try to let you know what I like about the solid design principles best. Now, as the curtain raiser for my presentation, I'd like to start with our giants are female, and the person I've chosen is Fabiola. She's very well known to the LabVIEW community. She is a LabVIEW champion. She is the lead architect of the DQMH framework, and she is also the co-author of the book on LabVIEW. Now, I say the book because there are many books on the market that talk about using LabVIEW as a tool for, let's say, data acquisition or for, digital signal processing and so on. But very few books on the market that talk about LabVIEW in and of itself as a programming language. And this is the most recent and updated one. And it also features quite a bit in my presentation too. She is both a teacher and an active practitioner of LabVIEW, which is a rare combination. So she mentors a lot of people. She has coached many people and so on. And she's also an active LabVIEW developer. And she's also very active in the community, and such as in open source initiatives such as the community training initiative and so on. And the main reason why I chose Fab here is because she is also very helpful and supportive. And this is something that I can say based on my own experience. And the best part here is if you take me out of the equation and put somebody else, they will also tell you the same thing. So that makes Fab even more Fab. So, and apart from work, she's also she's an avid ceramic artist, and that is her Instagram handle. All right. Moving on from Fab to somebody slightly less interesting, that is myself. I've been coding in LabVIEW for about 15 years now. I first started using LabVIEW in a research setting when I was working in neuroscience research. And I've used LabVIEW both at work and outside of work. Uh, Ultimately, my end goal was somehow to make LabVIEW my daily driver. So I've used LabVIEW in very disparate applications too. And last year, I decided to participate in some LabVIEW based competitions. So Summer of LabVIEW, to my surprise, actually, I did quite well, especially in the Wordle challenge. For the last few days, I was leading the leaderboard until on the last day, I dropped down to third by a whisker. Then also in the Advent of Code challenge, which is a global competition in the LabVIEW leaderboard, to my surprise, still I somehow topped it. All right, let's move on to the main topic of the presentation. We'll start with what design principles are. Now, design principles are basically a set of rules or guidelines that you're supposed to follow in order to avoid some easily avoidable bugs, or even if they're not easy to spot, they are documented. So if you follow these principles, then you end up with fewer bugs than you would have otherwise. And unlike design patterns, which cater to a specific problem, design principles are more general. Case in point is the solid design principles, which is the focus of this presentation today. We'll get to what each of these letters means, but they've been around for a while, at least 25 years. And also, they are language agnostic. So you don't need to be using LabVIEW to adhere to the solid design principles. You could go away from LabVIEW to some other language, which I wouldn't recommend actually. But if you go and start programming in Java or C Sharp or some other language, you could still, if you are using object-oriented programming, you could still use the solid design principles there to improve your code quality. So the question then arises, because they've been around for a while and they're not LabVIEW dependent, and even in LabVIEW also there are a lot of videos online. So why am I talking about them again? Uh, the main reason is that until 2020, interfaces were not a core language feature, and they are an integral part of the solid design principles, as you will see going forward. So because of that, and all of these older presentations, especially those that are LabVIEW centric, they had a set agenda sort of, wherein you start with the principles, then in between you have to segue into how, even though interfaces are not a part of LabVIEW, you can approximate interfaces using by reference classes or something of that sort. So because all of that is now not needed and interfaces are a core part of a LabVIEW, I thought it might be worthwhile looking into this topic once more. Uh, Ideally, we should be starting with what classes are, but in the interest of time, I'm going to just briefly mention what they are and then move forward. This is also the second time I'm talking on the same topic. I had spoken about the solid design principles in March 2025 at the Indian LabVIEW users group. So a re-recording of that presentation is available on our company website. So if you are interested to know more about classes, or at least my perspective on classes, you can please go ahead and look at the YouTube channel. So for now, the only thing I'll say is that a class is a cluster. To a first approximation, it's just a cluster because the class data is basically a cluster, but it's not an ordinary cluster, it's a restricted cluster. What do I mean by a restricted cluster? There is something called access scope. So even though you have data, the places where you can access that data can be defined by you and by using community, private, protected, or public scope. And that's just half the story, because you can also define functionality by defining methods, and even those methods can have their own access scope. So all of this gives us some characteristics of classes. Classes are, I mean, they have encapsulation. So to the casual user, the exact implementation of the code is hidden. Inheritance, you can extend functionality or modify functionality by inheriting from a parent into a child and modifying the methods there or adding new methods there. And then there's something called composition, wherein one class can be contained in a different class. I'm particularly fascinated by composition, but it's not going to be the focus of this presentation. So I'm going to just move on to interfaces. Interfaces, I'm going to be spending a little more time on. Uh, Interfaces, the formal definition is that they are a handshake agreement or a contract, which states that any child class that inherits from the interface, it needs to implement all the functionality that the interface says it is going to implement. That may sound confusing, so let's go with a non-lab view example. So in this case, I am now presenting here and I'm using PowerPoint. My colleague Faisal, he spoke on the introduction to DQMH. Those who are eagle-eyed among you, they might have seen that he was using Canva. So let's say this is a hypothetical discussion. This never happened in our office. But let's say that before the GLA summit, we were discussing that we are going to present, and these are the topics that we are going to present on. And I pipe up and say, I'm going to use PowerPoint because I like PowerPoint, the interface is smooth and so on. And my colleague pipes up and says, no, I would like to use Canva because I have more expertise in that. And at that point, our boss sort of interrupts us and says, hey, use whatever you want, I just want a good presentation from the both of you, right? So in this case, the boss is playing the role of an interface, only bothered with the functionality, not with how that functionality is achieved. uh, Another example of this is user interfaces. So whether you have a calculator, a laptop, a mobile phone, if I press the key, if I press the number 9, for instance, I know that the 9 will be displayed on the screen. Whether it's using the LCD crystals or using a capacitive display or whatever other LED screens, for instance, whatever it is, we know that if we are pressing a particular key, we are going to see that output. So as end users, we are also only concerned with the functionality, not with how that functionality is being implemented. Uh, in parallel, la- even with interfaces too, the outside world that is calling upon the interface is also just concerned that okay, is also satisfied with the fact that the interface is going to uh, implement certain functionality. How it is being done is not the concern of the outside world. So again, to extend our previous analogy a little bit further, so in this case, let's say there is another event where they have approached our company and said, hey, please send us a few presentations. So as long as they have communicated to the boss that please send us 5 presentations, for instance, they are assured that 5 presentations are going to come in, irrespective of what medium is being used. So like that, even the outside world uh, using the interface is only bothered about the functionality there. Now let us push this analogy one step further. Now we have established I am an employee of my company RF Systems, and we develop instrument drivers. So, and I have a boss who is mainly concerned about the functionality. So he is playing the role of an interface here. Also, we have clients who may come to us and say, hey, please supply code for us that is actor framework oriented, or uses DQMH, or doesn't use anything remotely object oriented, because we only like monolithic VIs. So the client in this case is analogous to a class, because they are concerned not just with the implementation, but with how the data is being used and modified. Now, how are interfaces achieved in LabVIEW? Uh, they are achieved by removing the data part of the class. So this is also seen in the iconography. You can see that there is a cube in a class, but it is not there in an interface. Similarly, so in an interface, you cannot define accessors for data. You can only define static and dynamic dispatch methods. Static methods can only be used to define some common functionality which cannot be overridden, like in classes. Dynamic dispatch methods can be used to define the connector pane, and they will form the contract of what the child classes have to implement. Now, there's a clarification here. So, when my basis for this statement, the last one, was that when I go and create a new interface, I have this setting wherein it by default says all overrides must be transferred to the descendant classes. However, LabVIEW does provide a facility to go and individually uncheck for each item or any item that you need that compulsion. So that way you can define some code in the dynamic dispatch method of the interface if need be. And if any one child class of say 10 needs to have their own override, then you can go and override it in that class. Other classes will use the dynamic dispatch method. So why use an interface then? The answer is whenever you have two separate classes or two or more separate classes that have different data types. So say one is using a file refnum, the other is using ActiveX refnum or whatever. So you can't have a common parent there because both the refnums are not the same. Similarly, if you have classes that do not have any data, so in short, wherever you used to use abstract classes before, you can use interfaces now for added flexibility. And also, you cannot inherit from multiple classes, whereas you can inherit from multiple interfaces. So if you need multiple inheritance, you will need to use interfaces. Okay, so all of this is well and good. Where does solid design come in? So object-oriented programming does help us structure our code more. It helps us to debug easily by giving appropriate access scope and so on. But it is still possible to write bad code. By adhering to the solid design principles, we have some safety nets, some guardrails to avoid the more common mistakes. But of course, first we need to know what they are. So finally, after all of these slides, uh, we are going for the solid design principles. Not yet though. One more slide later. A few disclaimers before that. Normally, solid design principles are dealt with in that order. SOLID, if you look up documentation online. What I'm going to do in the course of this presentation is talk about them out of order, hence the fluid part of my title. Also, I'm only going to be covering the surface and slightly less in depth, but not too much. So you will need to do your own homework to know more. Uh, First, we'll talk about what the solid design principles are. Then we'll look at the advantages that they provide. Right. So drum roll if possible. All right, let's start with S, which stands for single responsibility principle. Now, again, I'll start with an analogy. Let's say you have been assigned the task of recruiting gatekeepers for a compound. Now, if that compound is small, a single person is enough to lock and unlock the gates, even if there are multiple entrances and exits, and also do some rudimentary security check, perhaps. But if there are too many people, sorry, if there are too many people, if it's a large compound, you will require more than one person to do the same job that earlier one person was doing. So, based on the scale of your problem, even though the task is the same, the responsibility changes. In software, this translates to each module must have a single responsibility. What do we mean by responsibility here? Basically, it is a reason to change, for a module to change. What do we mean by that? We could, in principle, if so, in the next examples for all of the principles, I'll be using a multimeter so that we have a common example to see and compare the different design principles and how they are applied. So we could design a digital multimeter class wherein we put in every method, every property attribute of data that there is, and set the accessors for that. That is fine in some ways, especially if you have a large application and you have just a single multimeter that you're not going to modify later. That is okay. But more often than not, you will need to come and tweak the code. And when you have to do that, you have to come back to the same multimeter if you want to handle, say, how power is turned on or off, how capacitance is measured, how voltage is measured, how inductance is measured. Everything you need to come back to the same class and modify it. So this is equivalent to having a multi-tool with every tool therein. And while that is possible, it is not generally done. Also, as you can see from this picture, having too many tools in one overarching tool makes that tool brittle. So similarly with classes too, if you have, or even interfaces as well, which we'll get to in a bit, if you have too many things happening in a single module, it is susceptible to breakage. Before we move on to the next one, any questions? Uh, we are very good on time, so we can pause here if need be. Okay. So next from S, I'm going to jump to I, which is interface segregation principle. This, in my opinion, is very similar to SRP for classes, but this applies to interfaces. What ISP states is that one interface should expose only limited methods in its contract. It should not be too large, in other words. Why is that? In principle, again, if we have an interface, we could put every method that we need. And this is okay as far as the child class that is inheriting from the interface supports all of those methods. If that is not the case, if tomorrow we want to implement a simple multimeter wherein only voltage and current are measured, for instance, it does not have auto zero, it does not have sweep, all of those methods cannot officially be supported. But if you do not include those methods in your child class, LabVIEW will complain there will be broken run errors all over the place because remember every dynamic dispatch method in the interface must be supported in its children, right? So and even if you go and change that setting that the interface should not transfer the requirements of override to its descendants, it will I mean the API will still support the interface method where the multimeter will not. So that's a whole different problem altogether. Pictorially, if you have exposed too many interfaces, it means that it leads to confusion basically of what is to be used where. By the way, these motivational posters that are there, they are from LabVIEW Graphical Programming 5. I did not know of them before that. After I, we will again, any questions here? Okay, cool. We'll jump to the open closed principle. This in full, it stands for open for extension and closed for modification. Again, in my opinion, this directly follows from the requirement that our modules have a single responsibility and our interfaces be lean. Because of that, what happens is what we are encouraged to do is when we want to add new features, we should not modify existing code, we should only create new code. So, for example, let's say we started off with a simple multimeter, right? We only support voltage and current and power on and off. Now, tomorrow, if the company procures a fancy multimeter, there are two ways to go about it. One, we can take the simple multimeter class and rename it to fancy multimeter and add those different methods. The problem is in making these changes, we might break existing code. So the proper way to go about it is have your existing classes, and then if you have any new features, you just add them in a child class, so that if you need, I mean, you're not modifying any existing code here, right? Okay. And this isn't just for classes. Even if you have interfaces, you can have smaller interfaces which support basic methods on top, and have interfaces which support different methods at the bottom, and and yeah, child classes that inherit from them. If I'm not wrong, I think this was a mistake here. The attributes and accessors that are there in the child class, they should not be the same here. That was a mistake on my part. I'm sorry. So the analogy given here in the motivational poster is actually a bit gruesome. So if you just want to add a code to a person, you don't do open heart surgery, you don't open them up. So if you just need to add some new features, you just add new code, you don't modify existing code. Okay, we are finished with three. No questions so far? Okay. Next, we'll move to the Liskov substitution principle. What this principle states is what it basically is for is it governs the conditions under which a child can replace a parent in the code by using dynamic dispatch, for instance, and not cause any errors. What do we mean by that? Let's say we have a parent, which is an interface, and I'm going to move away from the multimeter for a few slides here, just to make this explanation easier. So if we have a parent interface and it has a method called generate wave, and we have a child which also has a method called generate wave, probably they were developed by two different developers or different teams. So the interface has on its connector pane time in seconds and the output in radians. The concrete class has time in milliseconds and the output in degrees. So because they are both doubles, LabVIEW will not complain if during runtime the concrete class is substituted in place of the interface. However, the results that we get are going to be erroneous. So this can lead to errors, or it can even lead to catastrophic consequences. For instance, there are two examples I've taken from one of the previous presentations on the solid design principles. The Mars climate orbiter crashed because two different systems used two different systems of units. So we had one which was uh, in the metric system, and the other in the imperial system, and that caused issues. Then the Ariane 5 rocket had an I-16 and a double in two different modules, and they were not handled properly. So the conversion just caused everything to explode. So, I mean, yeah. The thing about the Liskov substitution principle is that there are different subclauses. We'll go over them one by one. And there are more than what I've covered in the slide. But yeah, yeah, Sam. So uh, the few that I felt were important and applicable to LabVIEW. Number one, if you have a child and a parent, the inputs of the child should be either of the same type or more abstract than the parent. So let's say instead of a number or a string, you have a different classes as the input. So if your parent interface has class A and your child interface has class B as its input, and B inherits from A, that is valid, because when B is substituted in place of A, the wire there is going to be of the parent, and therefore it's going to be more abstract. And if you remember from object oriented programming, a child can travel along the parent wire, not the other way around. So if you have the child input being uh, you know more concrete than the parent input, that will just cause errors there. On the opposite side, the output of the child should be more concrete than the parent, or rather the parent's output should be more abstract. Again, it's the same thing. If you are when the child is substituted in place of the parent in order to avoid the errors, the child should be the output of the child class should be the output there. And also, this is a bit important, the child method should not throw unexpected errors. What do we mean by that? Let's say your parent interface or parent class, the contract says that it supports values 1 to 100. The child class supports just 1 to 10, for instance, and generates errors for the rest of them. Now, because the contract of the interface says that it supports 1 to 100, if the input is 1 to 100, we may not be handling the error downstream. And if this error is generated unexpectedly, it might just cause issues in the program, right? So, and then going forward, the child should not strengthen preconditions. What do we mean by this? Preconditions are inputs, actually. So similar to the previous example, if the input of the parent is all integers and the input of the child is just positive integers, again you will have unhandled errors and exceptions. So that is something to be avoided. Then child should not weaken post conditions. Post conditions are outputs. So if the child supports all integers, whereas the parent supports only positive integers, so this is the opposite of the previous one. What happens then is, if the downstream API is expecting just positive integers, whereas the child supports all integers, we might just have some unexpected inputs which can cause errors. So all of these are basically different ways of saying that when you have your inheritance tree, it should go from leaner at the top to more and more heavier classes and interfaces at the bottom. So if you see from this inheritance tree too, you will see that your parent interface has just some basic methods, and your fancy DMM interface has more methods and more, and the concrete class 2 has more methods and properties. So what this also means is that there need not be a one-to-one correspondence between your parent and your child. A child can support more methods than the parent does. So pictorially, this is what the motivational poster said. Excuse me. All right. So before we move on, any questions here? This is the one that I personally find most confusing. So Sam had a comment earlier that said this is a case for using domain types instead of primitive data types. Okay. So moving on to the last one, which is the dependency inversion principle. Oh, we are going really fast. Huh. So this basically talks about how dependencies, how the calling code should not depend on concrete implementations, but on abstract implementations. And there is a reason for that. Let's say your calling code is a process class that has a concrete implementation of a multimeter, right? So in that case, whenever the multimeter code changes, it will cause a recompilation of the calling code, and it might lead to erroneous performances or poor performances too. On the other hand, if you have uh, something like this, wherein your calling code is contains in its as a part of its data and an interface, and the interface has a concrete implementation. At uh, in the source code, you see that the inheritance is going from bottom to top, as well as you have this process class calling your data interface. So the dependency here is like this. In runtime, however, even though it is calling the interface, the actual dynamic dispatch methods from the concrete implementation are going to be used. So there, the runtime dependency is going to be like this. So there's an inversion of dependency between the source and the runtime. And if we ensure that our architecture has such inverted dependencies between source and runtime, it helps make our code better in the sense that we can. Okay, 1 second. Yeah. So because of that, what happens is that we can easily swap out our concrete classes without modifying uh, our process, because we can just change we can just have a new class that inherits from the same interface, and somehow using factory pattern or something like that, just load that class instead of DMM, and our calling code doesn't change there. It is still the same. Okay, 1 second. All right, so this has a very good analogy. If you need to plug in a lamp to a socket, you're not going to solder the wires directly. You're going to use a plug. So that way, if you need, you can swap out the lamp if it's defective or if it needs to be modified. So using a dependency inversion basically ensures that we can do that. All right. So we have covered a lot. Let's take a quick recap. Uh, SRP, single responsibility principle, states that a class should have just a single reason to change. And this page is from the LabVIEW graphical programming book. And uh, please focus on the right side column because that is LabVIEW specific. So again, in this case, it's basically the same thing. It says that your classes and VIs or other modules should just have a single responsibility to change. OCP states that in order to add new features, you need to modify, you shouldn't be modifying existing code. You should only be adding new code. And the way to practice it, I feel, is very well summarized in the right side column. That is, uh, I mean, if you have your classes, just make them into PPLs. And if you need to add new features, then you cannot. I mean, it becomes harder to modify your existing classes, and you can keep that as a practice to how do you put it, to learn OCP or to practice OCP. Although PPLs I've seen on forums and on other channels, they are not very well received in terms of build issues and all that. But as a learning tool, I think they could be used here to practice OCP. Now, which was the next one? Liskov substitution principle. Uh, Try to minimize. So Steven's question is, if you find yourself needing to modify a class, should I just delete it and start over? I mean, there are going to be cases where you need to modify existing code, but the point here is to keep it to a minimum. So if there's a bug in your existing class, obviously you have to go and modify it. But if it is already working and you need to add a new feature, then you shouldn't be going and breaking something that's already working. So that is the rationale behind this. So this way, if you have some code in production and a certain number of customers are already using it, because you're not going to modify it, they will not come back to you and complain that whatever was working before is not working now. So that is the thing. Now, Liskov substitution principle. It states that subtypes must be substitutable for their base types. In other words, children should deliver on the promises that the parent states that it will be uh, that the parent states. Children can have additional functionality that the parent does not support, but it should not be the opposite way. So it should not be the other way around. So that also shows in the inheritance tree how the uh, children get more and more complex, whereas the parents are small. Now, interface segregation principle. It states that your interfaces should be lean and relevant. You shouldn't be having too many methods that the child classes will not be using. Uh, yeah, so LabVIEW programmers who are using your interfaces shouldn't have to wonder what these additional methods are and how to implement them, or have to use dummy VIs there. And dependency inversion, by having your dependencies, uh, by having your top level module not depend on concrete classes but on abstract classes, you make your code easily swappable and modifiable without having too many issues. There are two subtypes here. I've not gone into that though. uh, Again, so like I mentioned, this is just an overview. So okay. So Darren says modify the private VIs in your class all you want. Try not to modify public VIs unless you have a really good reason. Yes. So that way your public interface doesn't change and it still stays the same. So, and if this goes back to your Liskov substitution principle also. So your child classes can have more methods, more private methods that are used to implement specific functionality, which are not exposed to the public. And that way, I mean, that provides some certain advantages too. So if you have 1:1 correspondence between your interfaces and yeah, and there are specific refactoring patterns for that, is what Sam says. So if you have 1:1 correspondence between your interface methods and your child methods, any change that you have to make in your child, you have to go and modify the interface too. So that raises the question: what is the interface doing there in the first place? So to make your life easier and to make your code easier to modify come a later date, the interfaces and the basically the parent should uh, have be leaner. Again, I'm just stressing on that point again. Right. So we've covered the solid design principles. We've talked about classes, interfaces. So if you're hoping that this is the end, I'm sorry, it's not. We still have a few more things to cover. So as I mentioned earlier, we have covered what the solid design principles are. Let's look at what benefits they provide, because clearly, as we've seen through all of these examples, we are complicating our life. We are, making our architecture more complex. So surely there should be some benefits here. By adhering to the single responsibility principle, we ensure that because each module has only a single reason to change, in order to if we need to make any change, we know which module to go to, right? So we have I mean, limited places where we need to go and make a change. We don't have to go and change the code in 10 different places in order to see our total change affected. By adhering to OCP, we have minimal risk of existing code breaking. We've already covered this. And by adhering to the Lishkov substitution principle, we can prevent bugs that might otherwise be missed. By adhering to ISP, we keep the code base relevant. The interfaces are not bloated. They just support methods that are needed. And if need be, we can refactor the interface to have from a single interface to multiple interfaces so that they are lean and they can be used in a more effective manner. By adhering to DIP, because we are depending on abstractions, we can make changes much more easily, and the effects of any change are also more limited. Now, having said all this, how many of you are familiar with this quote? Should be kept in mind during the issue. Yeah, so Stephen asks, solid design principles should be kept in mind during the initial programming but followed much more closely after it is deployed in production. Well, if you're adhering to this, and this is my opinion. uh, if anyone has a different one, please feel free to pitch in. uh, I feel if you're adhering to the solid design principles well, uh, while you're during your initial design, it becomes easier to adhere to them after your code is in production too. So it's, or you will need to refactor your code in order to make them more compliant. But it's interesting that you have asked this question right now. Just wait for one more slide. All right. So this quote from Abraham Lincoln that states that you cannot fool all the people all the time. Basically, when I was reading LabVIEW graphical programming, the chapter on solid design principles, I came across this passage which states that it's very hard to adhere to the solid design principles all at once in the same block of code. Which I mean, initially, honestly, I was like, why was I reading this whole chapter and why am I preparing a presentation if it's not possible? The answer is still provided in that same passage, that if you know what the solid design principles are and you have good reasons not to adhere to break one of those principles, it's okay to do so, but you need to know what they are and why you're breaking your I mean, why you're moving away from that principle. So for instance, there was a post on LinkedIn by Hunter Smith, if I'm not wrong, wherein he did not use dynamic dispatch in favor of speed. So there, obviously, he would have to take care that there is no type mismatch and all of that, but it did provide some value. Similarly, if you have a big code base, it's not possible to stop everything and refactor everything so that it adheres to SRP. Sorry, I have a bad throat today. So because of all that, there are trade-offs. You might need to compromise on one of the principles in favor of the other, or just forego the solid design principles altogether if need be. So, I mean, it's a judgment call ultimately. But if you adhere to them as much as possible, it does help to prevent spaghetti code. All right, we're almost to the end. Uh, yeah, so Steven says this was starting to seem unattainable. Well, I try to adhere to them as much as possible, and I've seen vast improvements in my code. And not just with LabVIEW. Off late, I've been involved in CI/CD using Jenkins at work, and I've tried to refactor even batch script so that it becomes easier to add more features later, and it's really paid dividends. So what worked in one project could be ported very easily to a different project without me having to do anything apart from just copy paste a single file to a different location. So yeah, I mean, I don't know. I try to achieve the impossible in this case. All right. So there are plenty of resources that you can look at to understand the solid design principles better. As I mentioned, there are a lot of presentations by a lot of people. Uh, Especially Stephen Loftus Mercer was instrumental in introducing object-oriented programming into LabVIEW. So Dimitri Sajatelian's presentations were actually a revelation. I mean, they changed my outlook on the solid design principles and how it is implemented after watching them. John McBee, Alan C. Smith, they also have some really good presentations online. I've been mentioning the book time and again, but I'll still reiterate LabVIEW Graphical Programming 5th edition I mean, it has fab content. I keep saying that online too. And the best part about the book that I like is it doesn't just talk about something, but also gives you resources on what to explore further. So I loved that, and that really did help me learn more about the solid design principles. Now, after my March presentation at the Indian LabVIEW Users Group, Sam informed me about this other book called Dive into Design Patterns, and that has I mean, it has different examples. It has a very, I wouldn't say simplistic, but easy to understand explanations for them. And studying that also just helped deepen my understanding. And one resource that I would highly recommend is the last one. There is this gentleman by the name of Tim Corey, and he has a YouTube playlist which deals with solid design principles. Each principle is about an hour long, and the videos are of the form wherein instead of just describing the principles, it talks about. I mean, it uses actual code basically and shows how the code improves by adhering to each principle. So that actually, I mean, until I saw that playlist, uh, all of these videos and I had not read the book till then, my bad, but all of the videos that I had seen LabVIEW centric, they were not clicking until I saw this playlist. The only problem is that this playlist is C sharp centric, but if you just abstract out some of the details of how the interfaces are implemented in C Sharp versus LabVIEW, it is still a wealth of information. Finally, I would like to acknowledge a few people. My initial draft of the slides in March benefited from Fab's and Sam's reviews. Some of the slides are actually a direct consequence of their inputs. I had missed out a few things, such as the interface can have, you can have the option to not override a dynamic dispatch method in a descendant class. I did not know that until Sam had pointed it out. Fab also gave me some valuable inputs there. And in this presentation, I changed all the examples to make them more uniform. So the examples for ISP and DIP I used directly from Sam's code, and I'm thankful to Sam for giving me permission to use it. And similarly, Fab was also very welcoming in allowing me to use material from LGP5. So thank you to all of you. And lastly, my colleagues at RF Systems, they have seen the draft of this presentation in March now, and given me feedback on flow and outline and so on. And it really shaped up very well because of their feedback. So, any questions? And if anything occurs later, you can reach out to me on one of these avenues. I'm very active on Discord. Thank Christian. We have time, so we can wait for some more questions if there are. Steven is asking, can you go over the dependency inversion with a different analogy, something like the initial security patrol analogy? I am not familiar with what you mean by security patrol. I mean the initial security patrol. So um, as of now, I cannot think of anything. But if I do, I'll post it somewhere. So what I would recommend though is John McBee has a video on his website. I forget what the website is. Was it LabVIEW Craftsman? I'm not sure. So there is a presentation there that uh, does talk about the dependency inversion principle, and it's a different analogy. One thing that he uses there is, if you have a tool wherein you can, let's say you have a screwdriver for instance, where you have the same handle but you can swap out a Phillips screwdriver for uh, the normal flat-headed screwdriver and so on. So that sort of mimics your dependency inversion, because you're not directly holding onto the screwdriver that is fixed. You just the handle is the abstraction here. You can swap out the concrete tools as need be. I don't know if that helps. So there's a similar analogy on his website, and examples of some concrete code. Haha, okay, cool. But I will still recommend that you go and watch the video there. I should have linked that too here. I'm sorry. I'll get back to you on that. Also, a gentle reminder, 40 minutes later, I do have one more talk that also is solid design principle centric. So if I haven't bored you in these 45 minutes, please do join me there. So in that talk, I go through a practical demonstration of how I have used the solid design principles to improve the LabVIEW file API. And yes, I've not been able to use all the solid design principles, but some of them though. On that note, thank you.